Alright, so parallel capacitors, let's go ahead and draw them out. Parallel capacitor, if we draw our voltage source, would look like this. 1, 2, 3. Okay, so this one, let's just give some numbers. We'll say this is 120, 10, 20, 30. Alright, and so what I would ask you when I ask you to solve this circuit, what I would ask you to do is to find the the voltage across each capacitor, the charge stored on each capacitor, and the energy stored on each capacitor. So VQU, that's what I would be asking you to find here. So this is 10, 20, 30. So this is the little table I'd ask you to set up. Okay, and so I'll just put the two main equations we would use would be C equals Q over V, and then UC equals 1/2 Q times V. And we're typically going to actually use different versions of this one. So Q equals CV, or V equals Q over C. Alright, so just like resistors, what we are going to do is simplify the circuit. We're going to create an equivalent circuit, which would be composed of one and only one capacitor. We'll call that C equivalent. Now for capacitors, what you do for capacitors, well, an easy way to remember it is you're going to essentially do the opposite of what you did with resistors. So with resistors, when we had parallel circuit, we did the reciprocation, that method. Now we're just going to do the pure summation. So the equivalent capacitance for a parallel circuit is simply the sum. C1 plus C2 plus C3 plus whatever. If you have 50 of them, you add them all up. So for this case, it's going to be 10 plus 20 plus 30 equals 60. So that'll be my equivalent capacitance here, 60 farads. And again, you just bring over the voltage, 120. So just like we did with resistors, we're just going to solve for missing things. This time we're solving for V's or Q's as we go, and we're just going to work our way back into the original circuit. And at the end, UC is easy to calculate. By the way, notice here, the reason why the capacitance increases, if you look at these capacitors here, I could model these three as one kind of giant capacitor with a very large surface area. And if you remember our equation, C equals epsilon naught A over D, by increasing the area of this, what happens to my capacitance? It increases, right? And in fact, if these were all the same, if I tripled the area, what would happen to the C? We'd triple the capacitance, right? So that's conceptually, that's the reason why. All right, let's solve for missing things. I know V and I know C. What am I missing? Q. So we're going to go ahead and find Q. We could call this Q total. This would be just simply C times V. We're going to use this version of Q. So that's 60 times 120. 720. No, 7,200. Okay, remember the charge is coulombs. So this will be my total charge on all of them combined. Alright, then let's go back here. So just like with resistors, notice that each of these are completely connected up to the battery, right? 10, 20, 30 are all directly connected, which means what can we say is true about the voltages? They're the same, yeah. So that's one of the key concepts, and this is identical to resistors, is that all capacitors have the same voltage. So those two concepts are the same for the same reasons. So let's go ahead and fill that in. So this is 120, 120, 120. If I were to put a voltmeter across this whole thing, I would get 120. It's directly connected, right? So then what am I missing on these? The charge, yeah. So we're missing the charge across. So we're just going to go Q equals CV for each. So we have 10 times 120, 1200. We have 10 times 20, no, 20 times 120, 2400, and 30 times 120, 3600. Now you can do a mini check on yourself. What's the mini check? They should all add up to your total. So we calculated 720 or 7200. They should all add up to the total. Okay, last but not least, how do we find the UC? 1/2 QV. So be careful, you're not going to simply multiply these two. Don't forget the 1/2. We're going to take 1/2 of V times Q. So this is 72,000 joules. 1440 or 144,000. What's this one? 200 something? 16? Okay, and then we're done. We solved it.